Hi, I'm Forrester King, and this is my project for my fourth year robotics paper at the University of Canterbury. I did this with my good friend and lab partner Jackson Allred, and together we designed this UR5 robotic arm to make us a cup of espresso coffee. So how did we actually program this robotic arm? Well, we did it in a language known as Python, and we used a library plugin known as Robotic so that we could directly talk to and command this robot. Now, Robotic is a special three-dimensional software simulation environment for robots, and what it does is you have a one-to-one replica of everything you see before you on this table. So all of these appliances and the robot itself and the table itself is simulated in an environment where we can actually test out all of the movements that you are seeing it do right now. That way we ensure that we don't cause any damage to the appliances or especially to the robotic arm before we bring it into the real world and test it out. So what actually goes into programming a robotic arm? Well, it's a lot of mathematics, because you see, robots just see the world as a bunch of maths, as they see it as a three-dimensional coordinate system for X, Y, and Z, and a bunch of rotational aspects as well. So what we have to do is a bunch of special mathematics known as spatial transformations and inverse kinematics to tell the robot where it needs to be in space and how it needs to orientate itself within that space. So the spatial transformations is what we use to tell it to go from one point to another within space, and the inverse kinematics is what we use for the robot so that it aligns up each of its 6 joints so that it can move freely within space to a correct position and a correct orientation. Now, the hardest aspect of this project was when we had to do things known as homogeneous transformations. And this is where we take the global frame of reference from the robotic arm and we convert it into the local frames of references for each of the appliances. Now, what do I mean by that? Because that's kind of just a bunch of gobbledygook. So, the robot itself knows where it is, and it knows 2 points on each of the appliances relative to itself. However, separate to the robot, we have all of the dimensions of the appliances. So what we had to do was we had to combine those 2 frames of reference, so the local frame of the appliance and the global frame of the robot and the table, together. That way we combine them so the robotic arm can easily traverse into each of the appliances and say press a button or attach to a port filter, as you can see here. Now, that's pretty much it for all the technical aspects of this project. There was a few other small things here and there that we had to change, such as this tamper and scraper. It's not on the same Z-axis as everything else, so we had to do some maths to fix that. But most of the changes that we had to do and work from here on was just getting on the rig and making sure that our positions are the same in the real world as they are in our simulation, as everything's not one-to-one, so we had to do just lots of testing to make sure everything moves smoothly and all these motions were correct. But this part here is pretty cool though. So what we did was we converted the XYZ coordinates into polar coordinates, as this allowed us to have a semi-smooth rotation about the center of that 3D printed group head. As what was happening was when we were doing movements or rotations in Cartesian coordinates, we were getting these weird little judders and offsets from the central point. But when we switched it to polar coordinates, which is the coordinate system for circles or cylinders, it just got rid of that problem entirely, which I thought was pretty neat. So there's some other cool aspects about this project that I should mention as well. One of them is the UR5 robotic arm. It has these ball bearings on the bottom of it, and it uses a pneumatic system. So it fires air into the chamber with the ball bearings, and it sends them out, and it auto locks into any tool bit that you have. So here it locks into that one, and it just auto aligns itself using the ball bearings. And here we see the beautiful Joe in his natural habitat. Shout out Joe. This next part is a bit embarrassing. This is the one part and there's Peter. Hello Peter. So this next part we actually mess up as we had a collision with the cup stand. So what happened was we didn't get to test out this part, as it's one of the later parts in the series of movements, and we thought that we corrected for the cup height, but we accidentally had a collision here, so yeah, it talks out. Nothing we could do about it. It's all good though. I'm very proud of what we managed to accomplish in the time that we had, because, you know, it's not the easiest task, and we pretty much got most of it done. So yeah, all in all, I learned a lot, had a good time with Jackson, and yeah, we'll do it again. So yeah, that's about it, guys. Thanks for watching. The robot's just going to go through its last few procedures and finish making this imaginary cup of coffee. So yeah, thanks again for watching, and take care. Bye.